So let's look the key differences from IRS with the existing technology, that's your massive MIMO and the relay-based communications. Coming to IRS versus relaying first. So let's see what a relay does. So you have a base stations, which is here, and you have a relay. Relay is nothing but a repeater. We studied in our communication courses that there is a repeater, and although the relay name is not there when I studied almost 10 years back, but we studied a repeater, which normally does nothing but repeater. It amplifies the incoming signal such that you want to go to a longer distance. Okay, so this is the same as the job of the relay. So what it does, it has two varieties. For this picture, we focus on amplify and forward. As the name suggests, it has an incoming signal. For example, H is the channel strength from the base station. If let's say this is your base station and this is the relay, the channel is H here, the channel is F here. What do you mean by channel? This is your small scale fading parameter. Now, what is the incoming signal is H into Sn, and it will amplify by a factor which is beta, and then it has to traverse through the channel from the relay to the receiver, and the channel gain is G. So the receiver will receive a direct signal from base station and a amplified signal via the relay, which is this signal G beta HSN. Okay, so now what are the functionalities and advantages of relays? So, you basically the relay needs an active element, okay, to amplify and forward it. So it has an active element inside it. As active element meaning it will also amplify the noise. Okay, the noise amplification cannot be formidable here. The cost of putting such a relay will be slightly higher. Okay, and noise impact is, as I mentioned, noise is also amplified. Okay, and hardware complexity, yes, it requires RF chain. What do you mean by RF chain? That's your power amplifier, analog to digital converter, filter, all these processing techniques. So these are the major burden of why the cost of these active elements are going to be increased more and more due to hardware complexity. Okay, and the same thing, if we just see what's an IRS can provide, right? So here you can see that there is a communications which is a different, which is a RIS, which is reconfigurable intelligent reconfigurable intelligent surface or intelligent reflecting surface, the same name, but I mostly prefer IRS compared to RIS. Okay, but see what's the key feature in contrast to relaying here. So it is like a reflector. It will not amplify. Okay, so it has incoming signal H into Sn, and it has lot of elements. Lot of elements are there. Lot of elements in the sense these your boxes, okay, square boxes, and there will be a controller which is here. And they will give the command, okay, now you change your reflecting coefficients to this. Okay, so that thing controller job. Now IRS controller will set this reflection coefficient matrix big theta. Okay, so it will give you the theta. Theta is nothing but it will tell you what is the phase shift of these individual coefficients should be. Okay, depending on what? Depending on the channel strength of various links. And what it will do, it will H into Sn is there already as an incoming signal. You pre-multiply with theta matrix, and then there is a channel which is G from the IRS to the receiver. Okay, as before, you see G beta HSN. Do not confuse what is beta and what is theta. Beta is the amplification factor, and theta is something like it's a reflecting all the reflecting coefficients will put together and form the theta matrix. So when we will go step by step into system model and the equation, so it will be much more clear what's the job of theta here. Okay, now theoretically, what's the differences? So since it doesn't require any active elements, only the passive elements are setting. So you do not need to do this RF processing. Okay. Another advantage compared to these half duplex relays is IRS can give full duplex operation. You are transmitting and receiving at the same time. Okay, there is no need to do or wait. If I transmit, if I cannot receive. Okay, you do not have to wait for that. It's a full duplex operations, which actually will not give you the factor of half reduction when we talk about relaying. Your capacity is half of log of 1 plus composite SNR. But here we do not have this half factor. We have log of 1 plus SNR. Hardware complexity, as I mentioned, it doesn't require any dedicated RF element, dedicated RF chains, which is composite of DAC or ADC and so on. Cost wise, it is obvious that it will be smaller cost compared to deploying a relay versus deploying an IRS. The noise impact, it is not going to amplify anything, hence the noise is not going to get added or amplified, not boosted up. Next, what's the advantage of IRS compared to MIMO, massive MIMO, which we are now today telling, right? So massive MIMO base station is this one. Okay, it has hundreds, more than 64. Maybe you can think of more than 64 to 100 number of antennas. And it is basically placed a massive MIMO base station to serve the users via these beamforming approaches. The beamforming is nothing but you point the beam towards a group of users. There is a high spectrum, high intensity. There is a major low pointing towards this direction. Okay, you beamform another thing to serve another group of users. And this is possible. This is a one key advantage of massive MIMO. The cost is more RF chains. Okay, the number of antennas are increasing. So every antenna, theoretically, there is a RF chain in the behind. So you need to feed that signal, all these analog or digital elements to transmit the signals from this antenna. Okay, so more RF chain is the burden here. Of course, energy consumption will be more. Right? You are using multiple antennas. It will give you more hardware cost, processing complexity, and it will be also difficult to handle at high frequencies. High frequencies, of course, you can compact more and more number of antennas within a smaller wavelength, but also you need to circumvent this path loss, which gives more path loss when you increase your frequency range, which is the teragigahertz or millimeter wave. Let's see what IRS is giving us. So IRS is when I deploy IRS, where do I deploy first? Let's say there are buildings. So I will deploy on the facet of the tall buildings. You can see there. This is the outdoor scenario of IRS applications. We also come to indoors. So now this is the mobiles are here, your users are here. And we talk about not a massive kind of base station, but the base stations have some antennas. Let's say 4 or 5 antennas. It's a 4 antenna here. Okay, so compared to massive, we are in conventional MIMO. So we will not expect the MIMO benefit here. The MIMO has high spectral efficiency. It also reduces your probability of error. Now you see, you come down from massive MIMO to a 4 element MIMO. So then how you are going to compensate the other losses? That's the objective of this IRS. Okay, what IRS will do? It will, so a signal which is MIMO, here we can do the beamforming, and let's say we call it active beamforming. Now this conventional, the terminology I will be using active beamforming, which mean by your base station or the access point will transmit the signal via active beamforming. Okay, and the IRS will do passive beamforming. What the passive beamforming? I know the passive coming from the passive nature of the IRS element. That's why we call passive beamforming. And the passive beamforming will direct a focused beam towards these users. Okay, so now you are adding this advantage of IRS to make your network architecture to be low cost, less power consumption, scalability, and also we have to make sure it is compatible with cellular Wi-Fi and other standards. And you want to reduce your number of RF chains used for this network. So guys, that's the advantage of IRS. Now, this is theoretical. Okay, how do you prove IRS will give you this benefit? How do you compare the scheme? Okay, that's all we are going to study. So the main focus of IRS versus massive MIMO is it giving you flexibility, use substantially less number of antennas, which will give you less RF chain, less energy consumption, less cost. But you are going to incorporate something different on some to change your environment itself, rather than putting our burden at the user end or at the base stations, which are complex and which are costlier. Let the wireless channel to be configured smartly in such that we still get the advantages to the users as the massive MIMO used to do right now. That's called smart passive reflection. So where do we go? So we are here today, heterogeneous network. Professor Rajarsi has mentioned, we are talking about macro base station. We are talking about femto base stations, 10-meter size, very small. Micro base station, slightly higher but less compared to macro. Distributed antennas, relays, all are active elements. This is our heterogeneous network. Where can we expect? It's a hybrid IRS assisted network. You talk about a macro base station, you talk about different IRS elements, and you're still going to serve your users. So these are currently in 5G, and what we are thinking, 6G is a IRS assisted hybrid wireless network. We have macro base stations, lot of IRSs. And since they are passive, the interference from one IRS to another IRS will be very less, since we can pack them in less distance apart, which we cannot do for active element due to interference effect, interference mitigation. Coming to the differences, HeadNet, number one, macro and small base station APs, relays, distributed network. IRS will give you active base station, several passive IRS. Okay, high cost, low cost, not energy efficient, energy efficient. Active nodes requiring sophisticated coordination and interference management. You do not have to worry about it because thanks to the passive reflections of IRS. Okay, there is nothing that it is transmit, it's just reflect your signal. Okay, it is not the Snell's law of reflections. We have studied from our class 12 math. It's a Snell's law. Angle of incidence will be angle of reflections. Now we are going to change this angle of reflection smartly to get some benefit. Think of the advantages. Lot of advantages. So there is a scenario where you are talking about indoor. You place your IRS on the wall, and if there is a brick wall, the signal cannot traverse. Let my IRS and it will come to the users which is located to the edge. Cell edge connectivity for the outdoor. So there is a signal coming from base stations. There is a blockage here. There is a cell edge users. The signal can come from base station to the IRS and it will come to the cell edge user. How? We will ask these questions, right? We are going to see how. Physical layer security. What is a physical layer security? I will tell you in detail, but as of now, just assume there is a eavesdropper which want to overhear your information. And IRS reflections phase shift should be adjusted such that eavesdropper will not get anything or get very narrow or very thin signal compared to the legitimate user. Multi-user system, when you have to do a multi-user MIMO or multi-user setup, how this IRS will give you multiple access schemes. Doppler mitigations, when you talk about ultra reliable low latency, Doppler is a major impact. Okay, there also IRS can help. UAV, IRS can help. Vehicular technology, there is a communications between two cars. It can be done through the IRS reflections on some building. Localizations, you have to some GPS, the positions, the man is moving, you need to locate its positions. IRS can help through satellite. There are lot of advantages. Okay, will everything come true? Let's see one by one. Application number 1, coverage extension. We'll talk about indoor and outdoor. Okay, so what's our model? You have a source, you have a destination. There is no direct link. More often in outdoor situations, even if you have a direct link, better we will see as a case 2. Case 1, more prominent, no direct link. There is a IRS. So your signal is going to the IRS, from S to IRS. The IRS will do some smart job and it will come to the destinations. Let the distance from source to the vertical distance is dV and the horizontal distance is dH. And also let's consider there are n elements on the IRS. I consider only one IRS, a SISO system, single input, single output system, S&D, source and destinations, n element IRS. That is the simplest model we can think of. Okay, and the distances is DSD, DSR, DRD. For example, just to give some mathematical input. Consider a simple scenario, slow fading. We are not talking about Doppler, we are not talking about URLLC. Let's come to slow fading scenario. And flat, frequency flat, non-WFDM scenario, okay, which is the from scratch you will start. What is the received signal? So there will be lot of IRS element, right? So my signal will come to all the IRS element. It will get some extra phase shift and it will be transmitted back to the destinations. So what can we write about the received signal at destination? So this is my R, the received signal R, which is the transmit signal is PT. Okay, so when we write the signal amplitude, we will have write this equation like this. So if the summation is over this IRS n element I equal to 1 to n, you have your X is your input. If first is you will multiply HSR. Okay, the I stands for, let's say this is my ith element HSR. You have a e to the power j phi because I model my phase shift. Okay, practically speaking, this will be beta I into e to the power j phi I. Okay, now let's say for now to get some intuitions, let's say I assume there is no loss in IRS reflection. Loss in the sense there is no attenuation loss. Let's say beta I, which may be less than 1, but just for simplicity, assuming beta I equal to 1 for all the I values. So I'm just worried about e to the power j phi I. It will be again going back HIRD, sum over all, and there will be an AWGN noise at the destination, the receiver, which you cannot avoid. Okay, now the channel fading coefficients, I want to see there is a phi already sitting up here. Now HISR is alpha I into e to the power minus j theta I. I can write this in the form amplitude and phase. Similarly, HIRD I can write in this form. Putting together, how you can write in terms of amplitude and the phase term, alpha I, beta I, e to the power j phi I minus something, right? Phi I minus theta I plus psi I. You can see this. Okay. So now I see that where is my phase? The phase is all putting together delta phi I. And where is your amplitude? Alpha I, beta I. There are n number of elements. Okay, so this is your received signal. Now the job of the IRS controller, it has to tell you what will be the optimal value of delta phi I such that your SNR at destination will be the maximum. And remember, that has to tell once in a coherence interval, because that is a function of theta and psi, and that is the channel, and that is changing over in a coherence interval. So over in a once in a coherence interval, the IRS controller need to update the delta phi I such that you will get maximum SNR at the destination. First level of attack. How to maximize the SNR? You write your gamma. You write your gamma from these expressions. This is very simple math. And you do a mod square. So this is your SNR. And what is N naught, which is the variance of the AWGN noise. PT is the transmit power. You can see the term which is controlling this. These are all amplitude. The term which is controlling this is the phase. And you know, e to the power j into theta is always less than or equal to 1. And this is equal to 1 at theta equal to 0. Right? So I can get maximum SNR at what condition? When your delta phi I is equal to 0 for all I. And that essentially will give you delta phi I equal to 0. So your channel, the IRS phase shift, this is the IRS ith element phase shift, right? And that has to be equal to summation of theta plus psi, and theta plus psi is your channel to SR, and this is the angle of RD for the ith element. So that's my first level of understanding. Substituting back, I will get the instantaneous SNR maximum value, where this will be only 0 or this will get 1. E to the power 0 is 1. So you will know what's your maximum SNR. Those are interested in theoretical evaluations, they will do a lot of paper publications using the instantaneous SNR. Find the PDF of instantaneous SNR. Once you know the PDF, you can do a number of things. 3 different papers. Very simple. Just you have to think from the scratch. Okay. So this is already published. You can see the peoples are working down the line 5 years, 2021. This Bazar is the one of the big boss in IRS, published here. Okay. They started very simple model. What you can also think at your home. And they have published the paper, Modeling and Analysis of Reconfigurable Intelligent Surface for Indoor and Outdoor. What they did? See the benefits. Okay. So if I have to compare the performance of IRS aided system, I have to compare the performance with respect to without IRS. Okay, what do you mean by without IRS? So let me just repeat. You have a destination, you have a source. Now, when there is a strong direct link, I will also consider this is my one method. There is a strong line of sight which is shown by LOS. UMI, LOS. What is UMI? Urban micro. They have considered 2 different models for different frequency, one at 2.4, another at 28. MM wave, conventional below 6 gigahertz. The method number 1, line of sight. Method number 2, let's say you do not have line of sight, you have an non-line of sight path. That is your urban micro NLOS, where it is here. Where is my LOS? This is my LOS. And where is my IRS? Now, let's say there is an IRS, which is my point of interest. Now the signal will traverse via IRS. Where is my IRS? These are all red lines. So what is your expectation? First, see what we are trying to plot. It's a path loss. Path loss versus the distance. DH stands for the distance between the source, the horizontal distance between source and IRS. This is your DH. Okay, they plotted for two different frequencies. Now the path loss is the maximum when we talk about non-line of sight without IRS, which is as expected. There is no IRS, no direct link, you will achieve greater path loss. And the path loss is increasing if the distance between this and this is increasing. Okay, so consider there is no IRS and you assume the path loss should be high. Now you assume that there is a line of sight, the path loss will be the less, which is also obvious. And if there are IRS, depending on what number of elements you are there, for 64, this is my n equal to 64. This is my 256. So you can see there is a reduction in path loss, which meaning you will get at high receive power. Okay, path loss is more, meaning receive power is less. Path loss is less, meaning receive power is more. And if I increase up to 1024, my path loss is further reducing. And it is going towards the kind of LOS. And hence, we can tell with sufficient number of IRS elements, it is possible to touch this LOS curve. Now coming to high frequency, these advantage will be there, but not to that much extent. What you can see, these trends are same, but if I increase the IRS elements, I am not getting too much of benefit initially. But if I increase to much higher value, 4096, I will increase, I expect a greater amount of path loss reduction, which is expected because high frequency you have more path loss because the signal cannot traverse at millimeter wave. Compared to this, there will be a lot of other atmospheric absorption. So to summarize, we can see what is the IRS role in path loss reduction. We talk about two frequency range, we talk about different IRS element, and delta PL is the reduction of the path loss, which is the gap from this black dot from the non-LOS side, non-LOS to IRS aided. You can see as IRS element increases, the delta PL increases. And the communication engineer are very smart. They can compute the path loss exponent from the formula PL equal to PL D naught plus 10 eta log D by D naught. Okay, D naught by D. So you know the simplified path loss model, which relates your path loss exponent, and as my delta PL increases, which meaning your path loss is reducing, or similarly the path loss exponent is decreasing. Okay, they have measured the path loss exponent. When you are increasing your n, it is very clear that this is reducing. So IRS is helping to reducing path loss exponent, which is a great advantage. In 28 gigahertz, you can see the path loss exponent is reducing, but not to that much extent. It's simple 3.15, 3.13, 3.03. So what can we summary? That greater path loss reduction at 2.4 than 28 gigahertz. As number of IRS element increases, path loss exponent reduces. So will not it convert the wireless environment into a controllable entity? That's your breakthrough. You change your wireless environment rather than changing base station or the user equipment. No one has thought about this. It's a very, very nice and excellent idea if you can implement. Coming to scenarios. Now I will talk about coverage extension. It's an indoor setup. There is a source, there is a destination. Okay. So the situation is something like this. The source and destination is blocked. There is a wall and there are risk elements sitting in this wall and this wall. Okay. There are different rooms maybe. And the element wall, this is sitting. So signals is going from here and coming to this. And also the same time signal is going to here, reflect and coming to this. You will get two signals added. There is no direct path. Fine. If there is a direct path, it will also come a third signal and all of them will be added at the destination. If you want to have, if you have more money, deploy more IRS. Let's see. So if you can see, there is a source, there is a destination, the signal is coming via multiple IRS reflections and you have lot of signals putting together. Okay, if you more number of IRS elements are there. Okay, now the paper that I talked earlier, they did an excellent thing. They computed error performance under multiple IRS setup to give you some number where we can go at. So error probability expressions with this setup where you have NS number of IRS, NS, and each IRS has N reflection elements. The error probability is something like NS into N whole square. Okay, you can see the term here, NS into N whole square and e to the power minus this. So as this is increasing higher, it will decay faster. And there are other elements which is coming from Raytheon K fading, PPSK constellation, power, AWGN variance, path loss, and so on. So my takeaway is this. I have highlighted it. As the product increases, error probability decreases. So I need to see my product NSN. So let's say I talk about an indoor scenario where I cannot install large IRS, but I can divide the large IRS into smaller bits, multiple small IRSs, and it's fine. You can put one IRS with that many reflectance coefficients, or you can put NS number of IRS, each with N reflection coefficients. Both of them will give you the same error probability. So it will give you design flexibility. And multiple small size IRS can be best suited for an indoor environment. Talk about outdoor. Okay, so there is a source, there is a destination, the path is blocked. There are bricks and walls and buildings. No direct link. What you can do at this scratch? Let's talk about double IRS. Obviously, you cannot cover only with one IRS. It also might be blocked. Can you do something like, a very simple idea? You put one IRS close to source and one IRS close to destination. And there might be a direct path from these IRS to IRS. Okay, these are also hoping. If you do not have multiple things, you may have to use another IRS, and finally coming to this. But just to get some hands on what's happening theoretically and mathematically to compare our intuitions. What will happen? We have to do some math. Otherwise, you do not have any proper justifications how this will be going to affect your performance analysis. So just start with have double IRS, okay, to coverage extension. Now, if you are not happy, I will give you another option. You can have a choice. You have a group of IRS at the source and a group of IRS near to destination. So you have a multiple IRS to choose from. Okay, you can also select, or you can use the flexibility of transmitting through all the IRSs. So what we will have, you will get a lot of signals coming here. You can see this is coming here, here, or here, or it can come also here and here. So we'll have options. Okay, now what we are trying to achieve? Let's say if you put your IRS, can you try to cover the cellage users? Okay, that's the reliable transmission is possible for cellage users by putting more and more IRS. Obviously, there is no free lunch. You have to compromise. There will be complexity. To control all these IRS phase shift elements, if you are including more and more IRS, you have to keep in your mind, I have to adjust the phase shift suitably. Otherwise, I am not going to get benefit. People are also smart. They talk about selections. You don't have to worry. Just like relay selection, select the best node here. Select the best node here. Then you are coming multiple IRS to double IRS with the best option possible. Okay, that needs a lot of mathematical tools, optimization tools. We need to worry about this. But the message is, yes, it is possible for outdoor to cover extension coverage and also for cellage connectivity. Okay, the people we are at the cellage, are they be covered by the base stations via multiple IRS? Okay, so this is one directions people thought, coverage extension, the first step. Second, I will talk about physical layer security. So maybe I will try to give the questions answer at the last. Let me first finish because I very not good at time management. I will give the question answer at the last 15 minutes. Okay, just hold on. You can keep chatting in the chat window. You can keep posting, but let's cover this first. Okay, so second topic we are going to cover is physical layer security. So first, see what is security, what is physical layer. There are two terms, right? This is something might be new to a lot of you. This is physical layer and security. When we do mean by security, we mean the authentications, encryptions, decryptions algorithm. That is your one cryptographic way of meeting security. And we are talking about something more, that physical layer, security achieved in the physical layer. So to start with, let's give a quick overview of your basic, what do you mean by secure communication, your cryptographic way. Now, what you will do, you have to do something, right? You are going to secure your message before transmitting. So people will opt for encryption, decryption, and a method. Now, what's the encryption method? So basically, you are going to use some keys to transfer your plain text message to ciphertext message, which is unreadable. Your plain text is your data. You are using some keys to convert it to ciphertext. And at the receiver end, again, I will use decryption algorithm with the help of a key, again a key, and convert back to plain text. Now, depending on your key mechanisms, you have three different set of cryptography. The first is the secret key cryptography, where we talk about using private key, same key at the encryption and decryption. A single key will be used. Second is public key cryptography, where we talk about encryption using a public key and decryption using a secret key, and they are distinct. Okay. Also, people uses the third category, which is hash based crypto, and it is something like a function that will change your plain text to ciphertext, and it is not reversible. It cannot get back to plain text from ciphertext. So it's called one-way cryptography. Okay, I'm not good at all of this, so let me not to go in depth. If you are interested, I have to go into the cryptography based secure messaging system. Okay, this is the normal approach of meeting your security in communication. There are some limitations. First, require extra resources for computations. Okay, you have to make your cryptographic algorithm to be really secure enough, or you have to a brute force attack and all things will not able to break the algorithm. And for this, it has to be computationally extensive, energy inefficient. Okay, you need high computing power. Require delay for computations. Of course, when we talk about reliable, ultra reliable, low latency kind of thing, this delay of the order of nanosecond, very crucial. Okay, quantum computing. So down the line, we are thinking of our supercomputers, which will rely on a lot of physics background. If you are good in quantum mechanics, I will advise to look into this area. You will be much more interested in quantum computing, where your conventional encryption decryption algorithm will not hold. So what's the way out? Okay, one option is do not rely only on end-to-end cryptography. Rely something more. That's why we top-down approach, we come application, transport, network, link, physical. We are here, physical layer engineers. Can we think of out of the box solutions coming physical layer security? What do you mean by physical layer security? Okay, so let me go through directly. First, understanding the concept. Crypto. Okay, this is done in application layer. The signal is coming in the receiver end. Signal is coming from the channel. There is your channel. Physical layer, it do a lot of first is your decoding, demodulations, and it will, from the signal, it will do a lot of signal processing operations and it will give bits. Then it will go to the application layer where you will be doing your decryption algorithm using secret keys, and you have your secure message at your computer. You are seeing your webmail. That's your cryptography way of very simple looking picture. Now, if I want to map the corresponding picture and want to view what is physical layer cryptography or physical layer security, we will not say crypto, we will say physical layer security. You have to make sure your secure message is coming output of physical layer itself. And how you make sure the security is embedded? You have to do some smart techniques here. In the channel is a wireless media. So if I think of such a scenario, I put my dotted boxes, which is my major focus, to solely on physical layer. You have physical layer transmitter signals. Of course, there is a lot of other layers. I came down to physical layer. I transmit my signal. There is a channel. Interference can be added. There might be a lot of coding techniques, signal processing techniques, fine, which we can do handle at the physical layer itself. We will receive here. Now, security is making sure that the output of physical layer, we will get secure bits as compared to only bits in crypto. So if I make sure the bits are secured, I do not need to worry about secret key based mechanism in the application layer. Let them go as it is and we will get the secure message out of secure bits. Very interesting. How to do this? Okay. Before coming how to do this, I have one small slide putting your eyes together. Crypto versus FISEC. The cryptography assumes your eavesdropper, which wants to hack your information, do not have much higher computing power or limited computing power such that it cannot break the algorithm to decrypt. Okay, so it is only okay to have limited computing power and network knowledge for eavesdropper. If you go to the quantum computing, this crypto only will not work. So phi security will not have such assumption that eavesdropper has limited power or very high power. It will work for both. That's called everlasting security. But security achieved is challenged by ever-growing computing power for phi crypto. Extra burden, key management. Not possible for wireless ad hoc area network. You are at no fixed network ad hoc area. People are coming and joining and leaving. It's very difficult to maintain your secret key based management. FISEC, it's not required at all. How? Basic principle, encryption, decryption algorithms. Here, inherent randomness of wireless channel. Okay, I know wireless channel is noisy. Get that benefit into your hand. Get that noisy part in your hand and do something else on top of it. Okay, so see how it is happening, how FISEC works. So we have a Alice and you have a Bob, which is your source and destination, and there is a path, which is the message is going to transfer from Alice to Bob. Okay, and now there is an eavesdropper which is sitting here and it's trying to hack your information. It's overhearing the information. So what we are kind of ensuring, how we are going to ensure that's separate story. But as of now, assume that from a layman perspective, I want to make my main channel from Alice and Eve to be very, very strong compared to the channel from Alice and Alice and Eve channel, which is the main channel. This is also called main channel or main link. I want to make the main link to be very strong compared to the eavesdropper link. It create almost perfect secure communications without relying on private keys. How? How to make eavesdropper channel more noisy? That's where all these techniques will be using. We can use exploit fading, we can use MIMO with beamforming, we can use friendly jamming, we can use our friend IRS, and also we can use coding. So here is the entry of IRS in FISEC. Okay, lot of works are going on. Now, let me, if I want to tell you the FISEC based performance, I need to know how people are going to evaluate the performance to capture the physical layer security. Okay, so here we go. There is a Alice, there is a Bob, there is a Eve. We have a main channel, we have a wiretap channel. People use wiretap to mint the Alice to eavesdropper channel. Okay, so if I talk about Shannon capacity, we have C equal to something like log of 1 plus SNR of the main channel. And if I use the capacity, so I can write CM and C wiretap. Here I will be using log base to 1 plus SNR of the Eve channel. Okay, this is my first, what I know from this, my basic math. Now we are looking into information theoretic way of characterizing a secrecy capacity. Now see what is happening. If the SNR of the main channel is high, if this channel is high, CM will be up. It will be high. If the eavesdropper link is also high, CW will be high. Now there is a fight. Will my main channel will be winning than the wiretap channel or not? If the wiretap channel capacity is high, then eavesdropper can tap your channel easily compared to the main channel. So it all depends on the differences. That's the way I introduce CM minus CW. Difference of main and wiretap channel capacity. And we want the difference to be greater than 0. I want CM to be greater than CW. There might be situations your wiretap channel is higher compared to CM. Capacity of CW greater than CM. You will have this element negative. Okay, there might be situations where CW is greater than CM when my difference will be negative. Okay, then what do you mean by that? I will introduce a term called secrecy capacity. In that case, I will say my secrecy capacity is 0. 0 bits per second per hertz. I am not going to meet the security constraint here if the wiretap channel is very high. Okay, so we have to introduce some techniques such that you can meet this constraint, that you want your secrecy capacity non-negative. Okay, with this background, there are a lot of works going on. FISEC, we have defined the secrecy capacity as a difference between capacity of the main channel Alice to Bob minus capacity of the wiretap channel Alice to Eve. Take a maximum value between 0 and this. It cannot go negative. That's why I introduced forcefully it has to be greater than equal to 0. That's the new notation for measuring capacity in a secure communications called secrecy capacity. This is number 1 performance metric. Number 2 performance metric, as you all know the conventional outage probability, you do secrecy outage probability. What do you mean by that? Secrecy outage probability. So it's like when your source or the Alice is transmitting at a rate R and that rate is greater than secrecy capacity. What will happen? If I transmit at a rate less than secrecy capacity, my information will be secure, or my error probability will be as less as possible. Not error probability in the sense of conventional thing, but when you talk about security measure, we call secrecy outage probability. Outage event will occur if R greater than CS. So it's a probability that your secrecy capacity falls below the target rate of Alice, which I mean R. Okay, secrecy capacity is below the target rate. And intercept probability, this is the scenario where C of the main falls below C of the wiretap. Your wiretap capacity is higher and you are going to, wiretap means Eves is going to intercept your channel. That's called intercept probability. So that meaning, will all time intercept probability will be 0? No. Depending on your channel strength, you will have intercept probability. You will have secrecy outage probability and secrecy capacity, which is non-zero. But our target will be to maximize this, to minimize this, and to minimize this by sophisticated mechanisms. Now we will see the role of IRS. Research problem for IRS to physical layer security is how you can adjust your phase shift elements such that you make sure your security physical secrecy capacity is maximized, or secrecy outage probability is minimized, or intercept probability is minimized. Okay, so I will answer all the questions later. It will distract our focus of discussions. Let me just continue the discussions. I will answer. Okay, now coming to the how actually you meet the physical layer security by using IRS. This is a very small concept to see. So let's talk about a scenario that you have a access point, you have a IRS, you have a user, you have a eavesdropper. Now, as the access point will sending the signal, so eavesdropper will get and the user also will get, and there will be reflected signal from IRS to eavesdropper, IRS to user. Okay. Now, what will be our goal? As I mentioned that there is a signal coming from AP to user, which is this, and IRS to user via reflections, which is this. If you can constructively combine the two signals in phase, then you will get a high signal at the user. And if you can do destructive at the eavesdropper, you will get a null or almost zero signal at the eavesdropper. Who will do that? The job of IRS reflection coefficient. Okay, so we have to make sure a constructive signal is there, constructive interference is there between the IRS reflect signal and the direct signal from the AP at the user, and a destructive interference will be there of the direct and the IRS added signal here, such that eavesdropper will get a very limited amplitude compared to the user, so which will get a high amplitude signal. How can you formulate the problem? So that's our optimization technique. So to maximize the secrecy capacity, which is defined by the differences and maximum, which is these notations, we have to do joint optimizations of IRS reflection coefficients and the active beam forming. When we have multiple antennas, we talk about active beam forming. The vector W is here, and the passive reflecting beam, passive beam forming vector Q is there. So your problem formulations is very complicated now. So you want to maximize logarithm of 1 plus main channel SNR minus logarithm plus 1 plus each channel SNR, which is the secrecy capacity, subject to two constraints. One is that when you do beam forming, you have to make sure the transmit power is not exceeding PAP, power constraint at AP, and we also have an amplitude of these elements 1. Okay, no absorption. So this is a slightly complicated optimization problem. The closed form solutions might not be possible. You have to rely, or you have to do some alternate optimization techniques or some suboptimal techniques close to the optimal answer. You can do brute force search, which will taking a lot of computational power. It's a lot of elements are involved. W is a vector, number of antenna size. Q is a vector, again Q is a vector, number of reflecting elements. So you have your search space is quite high. Coming up with optimal solutions might not be feasible always. Okay, so the paper which Ruizhang paper, another big boss in IRS, looks into secure wireless communications for this. Okay, IEEE wireless communication letter 19. Now, what they get that very good justification or explanation visually. So in that particular setup, they simulated the result, and what they plotted secrecy rate versus eavesdropper and Alice distance. Okay, now what in the x-axis I see DABH, DAB meaning the distance from Alice and Bob, horizontal distance. Okay, now they have taken a number of antenna at Eve is M. Okay, it has M number of antenna. Number of IRS element 32. Okay, fine. Distance between Alice and IRS is 50 meter. So Alice and IRS distance is 50 meter, and horizontal distance between Alice and Bob is 44 meter. They are simulations, you have to assume something to work with. Now, what I can see, some trends I can see. Secrecy rate, look into this plot and this plot first, which are the plot without IRS. Without IRS, this is for m equal to 3 antenna at the eavesdropper. This is for m equal to 1 antenna. So I can see secrecy rate decreases as DAB increases. Okay. Without IRS, at Bob is going far apart from Alice, obviously the SNR will go down and the secrecy rate will go high. Secrecy rate will go down because Bob is going away. So your SNR of the Bob, the main channel capacity will be less because it will have less SNR value, which will give you. So if your C main is less, then the difference of C main and CW is fixed. Alice and if SNR is fixed, I am changing only the distance of Alice and Bob. So the difference will go down because C main will go down. So I will get a downward kind of slope. What is the trend with more number of antennas at the eavesdropper? Eavesdropper will do more number of antennas. It's better for eavesdropper to hack. And the secrecy rate, so eventually in our terminology, in this case, CW will go high if M will be increasing. And the difference will go down. So you will get lesser secrecy rate when M equal to 3 than M equal to 1. Okay, now place your IRS and see how you change, how these things are going to change. And they do a very good thing. They place the IRS here and they are changing the Bob distance. And you know, the IRS is located at 50 meter and they see that when Bob is also located close to the same area and the parallelly to IRS, which is at a distance of 50 meter, I am getting a capacity decreases and it increases. You will get the trend, it's increasing. So this is nothing but IRS now is giving a reflected signal, which it's a strong beam. It's coming via IRS when your receiver is located almost in a vertical position of IRS. Around this 50 meter, which is the location of IRS to this. And if it is going further apart, it is also decreasing and this. Okay, and as the antenna increases, the same trend. But I can see without antenna, without IRS and with IRS, obviously with IRS is better. It depends, no matter of what is my distance. All right, we'll get something. Let me see another one. Secrecy rate versus L, number of elements, IRS elements. Okay, so here I will see that you will have a number of IRS elements and you have your different curves. So what the first thing we will see that first you see without IRS, which is without IRS, this one and this one. So without IRS meaning it will be a flat, it will not depend on number of IRS element. Second thing is with IRS. Now when is compared to different distances, when DAB is 20 meter, where is DAB 20 meter? This one. You see that it is increasing, but increasing at a slower rate. Even if you increase L, it is increasing at a slower rate. But when this position is something like this, here at 50 meter, you will see that it's increasing rapidly as I increase L. Okay, so when IRS and Bob is kind of on top of each other, I get more benefit if I increase number of IRS element. Third application is cognitive rating. Okay, so I have roughly 15 minutes of time. I am getting late, but we will see how much we can cover. So cognitive radio is another technology where we talk about the shortage of the wireless spectrum. Okay, so your wireless spectrum is limited resource and there are a lot of applications. It has to give the spectrum to do their transmission. Also, you will see that most of the time it is not utilized. The allocated spectrum is not utilized. And the cognitive radio will come up to, it will give you flexibility to use your spectrum, okay, such that there are two parties, one are primary, one is secondary. You have a primary base station, you have all the primary users, and there will be some secondary users. Secondary user will take advantage of primary user spectrum. Okay. And there are different modes of operations. We will focus on underlay mode of CR, where when the primary users are transmitting, secondary users are also transmitting, same time, same frequency. Obviously, there will be interference from the secondary to the primary and also from the primary to the secondary receiver. So there will be interference constraint. Okay, your secondaries are allowed to transmit at the same time of the primary, provided they meet the interference constraint. And that interference constraint will not allow you to transmit at very high power. You have to regulate your power, the secondary. And these power reductions will limit the performance of the secondary user talking with secondary receiver. Okay, that's another problem. IRS will help. There is a IRS, there is a secondary transmitter, secondary receiver. This is my primary network. This is my secondary network. IRS is there to help the secondary communications. And of course, there are interference link from IRS to primary receiver, primary transmitter to this, and so on. Now my problem is to jointly do some optimization such that you want to maximize your data rate at SR, secondary receiver, or minimize the symbol error rate by jointly optimizing the reflecting elements and controlling the power. Because I need to moderate my power to meet the interference constraint. And I need to moderate or control the reflecting element to get a signal which is strong enough here, but to have less significant here, such that my IRS will not cause too much interference at the primary receiver. Okay, so this is another good problem you can look at. Your team are looking into this. You have a case too that is already there in the paper where they talk about a very complicated setup. You have a lot of primary users and a lot of IRS element, not only one, n IRS element. You think of a scenario where IRS are there to help the secondary and there are multiple red link, the interference link, and the blue link are the communication link. This is my secondary receiver. And they did a joint beamforming transmitter and IRS reflection coefficient adjustment in order to maximize the rate at SURX. Subject to the constraint, beamforming have a power constraint. IRS have mode of this beta will be 1. Right? So they have two constraints, and also you have an interference constraint due to the cognitive radio setup. You cannot exceed your interference to the primary receivers. Your I should be less than a threshold ITH for all the primary receivers. This is an additional constraint due to CR. People also think of IRS selection as same as when you talk about coverage, we talk about IRS selections. Here also people think of IRS selection as an extension to this problem. The last part is the UAV. So where my UAV can be applied? UAV can be applied in different varieties. It's an aerial base stations. It's going to serve different users. It's a relay where Alice is sending to relay and it's sending to Bob by a UAV relay. Or it can be gathering informations from users. Okay. So with this, let's see the use cases. It's a lot of this military, medical, and all those things. Advantages, of course, low cost, flexible deployment, then deploying a base station over there in mountain region. Disaster, obviously UAV will be better solutions. High mobility. Challenges, trajectory design, where do I place it? Optimization problem. Limited battery capacity, it's a very major concern. It's draining the battery power. You have to thought about green UAV. Okay, UAV network coverage. Okay, they are the IRS entry. IRS are helping to get more signal strength from the base stations to the UAV. So I will focus on two scenarios. One is IRS is helping for the downlink communications from UAV to the users. This is UAV based downlink communication. This is like a flying base station. Lot of users are there. You have a RIS. Its signal is reflecting via it, and you have a direct path and you have an indirect path. You will get better signal. Okay. So now see, IRS is assisting UAV in communicating with multiple ground users. Fine. What's my problem? I am including one more IRS. How it will give better performance if I have IRS versus without IRS. So when you do not have any IRS, your performance is flat with number of IRS element. Obviously, do not have any IRS. Your sum rate, we are talking about sum rate of all the users. Is this. Okay, now the sum rate will be high, of course, when you have a random scheme. Random scheme in what sense? Okay, before this, what is the scheme? You are going to optimize the IRS reflection coefficient and UAV trajectory. Okay, the problem is now UAV trajectory optimization and IRS reflection coefficient optimization, such that you want to maximize your sum rate of all K users. Now this paper proposed method is this blue line, which outperforms a random selection of elements and trajectory. Okay, this is a big advantage they are gaining when the number of elements is higher. Okay, and significantly it's going up. Red line is random. This is without IRS. Okay, better. You can place your UAV to communicate between, you can put your RIS to communicate between UAV and the ground users. Case 2, IRS for assisting aerial UAV. Aerial UAV users, meaning these are my receiver. Who is your transmitter? Base station. It is not getting a direct line of sight path, is very weak. In these situations, my signal can go via IRS, which may be on top of some building, and it will receive the combined signal. And in this case also, there are a lot of scopes that IRS will give benefit for aerial users. Okay, so the problem is control the phase shift of IRS and the directions of reflected signal such that UAV get a strong non-line of sight signal. Okay, now how to, and also the problem is where do I place my IRS, at what distance apart, on what building, and what altitude. What is the altitude of UAV? A lot of other things going to matter here. Okay. So I will show you a quick one plot here. So IRS gain, we can see this. So this plot is telling it's a base station antenna which is tilted towards the ground users, and you have all these IRS. So it's kind of going to give you a picture. Where do I place my IRS? Which building should I select to put the IRS? So it is telling as IRS distance from the base station is smaller and smaller, you have to put your IRS at a slightly higher height. Okay, your IRS should be putting in this zone, in this gray zone here. So if it is far apart building, slightly small height, which is very obvious, which is its beam is coming like this. So your IRS will be on this region. And this is pictorially showing here. You take two different IRS height, 5 meter and 10 meter. The 5 meter is this one and 10 meter is this one. The height of the 5 meter is smaller. The 5 meter height is the HIRS is 5 meter. Okay, it is the height of the IRS. So it has to placed farther apart. The distance from base station is farther apart from the 10 meter where this is 50 meter. Okay, so which is also obvious. Which is at a smaller height, it has to locate at a slightly higher distance. And what distance? You will get a optimum value, the peak value. The IRS gain, which is the without versus what is the signal, received signal power with and without IRS, the relative ratio. Okay. So impact of UAV height is not that much. It's telling that if you fix your IRS properly with height and distance from a base station, now you are changing your UAV height. It is not giving too much of major difference in IRS scan. So indicating height of the UAV has no impact on the selection of the building to deploy the IRS. Okay. So with this, let's see all the advantages in glance, and we covered three or four of them. And you have a lot of exciting research going on in this IRS. And let me summarize this. So we are talking about smart and reconfigurable IRS to change your wireless environment. In the future, we might see an IRS is sitting in your airport or shopping mall or in traffic road. It's a big building, or in indoor on the wall. No, how this is feasible, okay, or the research, proper time to do research right now. Okay, we can see it's very different from massive MIMO relay. It will do energy efficiency, it will save your energy. It will also give secure and sustainable communications. And we have looked into this potential use cases where we talk about this 4 use cases. Yeah. So now coming to the questions, from where I have to start. $11:45. So I have to start from 11:3, 12:3, 12:1, 12. Okay. Okay. Can multiple base station use the same IRS? Can multiple base station use the same IRS to direct the signal to differently directed users? Interesting question. Multiple base station use the same IRS. In practice, multiple base station are not co-located. Okay, one base stations and another base stations, you have a geographical separation. So in practice, separate IRS for separate base stations, depending on your scenario. If there are talking about an indoor kind of setup, it might be feasible. But for an outdoor, multiple base stations will not be using the same IRS to direct the signal. Should there be a okay, this I think Professor Rajarsi has answered. How will the impedance of each reflecting surface change and depends on what parameter? Okay, so it comes under the scenario of impedance change and all. So the parameter is the channel. Okay. The IRS controller will sense, so in the next step, I will tell you how the channel estimation is done. Basically, you need to capture the channel phases. Depending on the channel phases, you need to monitor what will be your theta I, that the controller has to tell the base station and IRS. How the impedance is changing, that is a question of a hardware perspective. They will be worried about changing the varactor diode resistance, varactor diode base change. That's not our concern. Okay, but we are the physical layer engineer will be seeing, depending on my wireless channel, how can I control the reflection coefficients? And in the VLSI people will tell, okay, if you have to control this, how can I change the impedance of the varactor diode to actually get my job done? Okay, so I cannot answer this. Is it possible to change IRS parameter, not only the number, so that the hamper IRS parameters in the sense IRS parameter? The IRS parameter is, we are talking about the number of IRS elements as such, but you can also incorporate more number of IRS. Okay. And you see the frequency relationship is different. When I talk about millimeter wave versus normal frequency below sub-gigahertz, the two entirely different. We have to think about putting how many IRS are required and what are the elements should be required in different frequencies. I do not know what is a MAB algorithm. Sorry. is it possible to use IRS for co-channel interference mitigations in full duplex small cells? Yes. So IRS are basically using in interference mitigations also. Okay. When we talk about full duplex, there is an interference for sure. And when you talk about co-channel interference, IRS can be used like that. We are also talking about similar situation in file security, such that even if we want to make sure the channel coming to the eavesdropper is relatively less stronger compared to this. So this also, the job has to be done by IRS facet. When we talk about a scenario called interference mitigations, you also have to look into similar kind of problems. How can I mitigate the interference? Okay, yes, it can. I do not know what is MAB algorithm. Maybe you can IRS selection. IRS selections, okay. I can only tell what people are currently using for IRS selection. It's very simple, like a relay selection. You have lot of channels. Now the question is, which one do you pick up? The simple answer is which will give you best benefit, which will maximize the SNR. If you talk about a scenario called cognitive radio, if you have two IRS, you have to look into the best SNR at the destination, subject to you have to meet the constraint. Okay, so the constraint might be meeting with full power. Let's blast the primary receiver with full power. Full power meaning meeting the constraint. If I tolerate to hamper the primary with 10 dB of interference power, you can do that well and choose the IRS which will provide maximum benefit for secondary. Okay, any further question? I think we are almost time 1:15. The point-to-point of millimeter waves using IRS is intended to reflect millimeter wave. As I told, it will be a very good applications to put in millimeter wave, because there we have to really worry about coverage extension. Millimeter wave coverage extension can be done through IRS. Okay, now the problem is the channel estimations, all those things that has to be worried about. Multiple beams, yes, you have to worry about how do you do beam forming at millimeter wave. That will be different from your this thing. So there is a research going on millimeter wave IRS deployment. Recorded video, we are trying to do it. We will see this. Channel estimation will be covered in session 4. Yes. Okay, the impedance one I cannot answer, Nishu. So we have to see some papers where they are talking about IRS in electromagnetic propagation physics point of view. There actually you can get some more on implementation of IRS, or how do you change the reflection coefficients practically. Okay, I think I am done. So